Hey there everybody. In this video we are going to attempt to tackle Einstein's theory of special relativity, which, like everything else Einstein did, was creative and fundamentally changed the way we view the universe. Specifically in this case, we fundamentally change how we think about space and time. We've always thought about those things as being absolute, but Einstein's theory of special relativity says that they are not. And the first thing we've got to specify is that it only applies to inertial frames of reference. Remember, an inertial frame of reference is a frame of reference that's moving at a constant velocity. So the general theory of relativity tackles those situations. We're just sticking to the special theory of relativity, and so we're only going to deal with inertial frames of reference. So let's first of all review what we already know about relative motion. We might refer to this as Galilean relativity after Galileo. And so this is kind of what we learned at the very beginning of AP Physics 1. Situations like this. Suppose you have a person riding on a train, let's just say that that's Annie, and a person standing at rest, let's just say that's Ben. There's our train. Now let's say the train is moving towards Ben at 100 meters per second. And then Annie, for whatever reason, throws a rock at Ben, such that Ben observes the rock to have a velocity of 80 meters per second. So Annie would observe the rock to have a velocity of just 80 meters per second, since she's also moving forward at a velocity of 100 meters per second. And so they disagree about the velocity of the rock. Ben's at rest, Annie's in motion. She sees the rock move slower relative to Ben. If she was moving at 180 meters per second, then she would be moving at the same rate as the rock, and it wouldn't look like it was moving. So that's relativity as we know it already, back from Galileo. But here's the next question. What happens if instead of throwing a rock at Ben, Annie were to shine a flashlight at Ben? Like she were to throw a photon at Ben. So here's what our picture looks like now. There's a flashlight, and there's a photon. Now, from Ben's point of view, that photon is going to be moving at c. Remember, c is 3 times 10 to the 8th meters per second. Let's just say that this is a ridiculously fast train that moves at a velocity of 1 times 10 to the 8th meters per second. And again, remember, Ben sees the photon moving at a velocity of 3 times 10 to the 8th meters per second. So if we were to only apply Galilean relativity, like we learned in AP1 to this situation, then we would conclude that Annie would have to see the photon move at a velocity of 3 minus 1, which would be 2 times 10 to the 8th meters per second. But the thing is, that's not what Annie actually observes. If Annie were to measure the velocity of that photon, she would see it move at a velocity of 3 times 10 to the 8th meters per second. Basically the same as Ben. So both of the people, in fact everybody, who observes this photon would see it have a velocity of 3 times 10 to the 8th meters per second. So our question for today is, how can two different observers who are moving at different velocities relative to each other measure the same velocity for something else? That's kind of what we want to try to figure out today. So first, let's discuss how we actually know that the speed of light is constant for all observers. There's 2 ways that we know this, and they're both equally important. The first way is theoretical. Back when we studied electricity and magnetism, we ended up talking about a dude by the name of Maxwell. Basically, all those electricity and magnetism equations were summarized in a set of equations called Maxwell's equations. And he predicted the existence of a wave which would travel at the speed of light. And so remember that these 2 constants here, epsilon naught is the electrical constant, mu naught is for magnetism. Remember, those are numbers. So that equation doesn't leave any wiggle room for relative motion. And so that equation says that the speed of light is always the same, regardless of how you're moving. Now, experimentally, we know this because two characters by the name of Kennedy and Thorndike basically took an interferometer, which is a device that can measure the speed of light, and they measured it in a laboratory in the same direction in January and compared it to their measurements in June. So in January, the Earth is moving in one direction, and in June, it's moving in the opposite direction. Remember, the Earth goes in kind of sort of a circle around the sun, and they showed that the speed of light was the same in both months. So the fact that the Earth was moving one way versus another way didn't affect the speed of light that they measured. So we can use those two things, kind of conclude the speed of light is constant. So Mr. Einstein, in his theory of special relativity, made two postulates with which he derived everything else. The first postulate that he made is that the laws of physics have to be the same in all inertial reference frames. Key word there is inertial. Non-inertial or accelerating frames of reference are dealt with the general theory of relativity. And then the second postulate is that all observers who are in inertial frames of reference have to measure the speed of light to be the same value. So no matter which direction you're moving or how fast you're moving, speed of light is always 3 times 10 to the 8th meters per second. So back to our original question. How can we use those two basic ideas to explain why we would measure the speed of light to be the same? And the answer is that we have to redefine how we think about space and time. So if the velocity's got to be the same for both observers, remember that velocity is displacement over time, so if that's got to be the same, then these two things must be different. And so let's discuss how those two things can be different. Let's talk about time first. Perception of time is often referred to as time dilation. The big idea here is that the faster an observer moves, the slower time passes for that observer. Now this doesn't have anything to do about perception or tricks or biology. It's not that you would age at a different rate or anything like that. It's that physically clocks run slower when they're moving faster. So here's kind of an example of such a clock. You can make a clock out of a beam of light. Basically you send a light beam which strikes a mirror and then returns to a detector, and in that time you can refer to that as one tick. So here's a simple picture of a light clock. We have a source, a mirror, and a detector. Let's just say the mirror is distance h from both of those. So in the frame of reference of the clock, the beam of light goes to the mirror and then returns to the detector. And if the clock is at rest, then that will be a vertical line. And so just kind of pretend that the angle's small there. And so the distance that it moves is 2 times h. It's got to go to the mirror and back. The velocity that it moves at is c. So solving for the time, we will get the time to look something like that. 2h over c. That's just some simple geometry. Now let's look at what happens if we're in a frame of reference that is moving relative to the clock at some velocity v, which would be the same as assuming that the clock is moving at some velocity v. That's probably an easier way to picture it. So if the clock itself were moving, then the observer, who actually views the light, would see it follow more of a diagonal path because the detector is going to be moving during the time that it takes for the light beam to travel to the mirror and then reflect back to the detector. So a picture might look something more like this. The detector is moving at velocity v. That means it moves a distance, v times delta t. Remember, delta x would be v delta t. And so the beam of light is going to follow a longer path. And so if it follows a longer path, that means that it would take longer from the stationary frame of reference for one tick, if you will, to go off on the clock. remember that the light beam still has to move at the speed of light c. So if we kind of do some fancy geometry, and don't feel like you have to write this down. In fact, you can stop writing for a few minutes. If we do some fancy geometry and create a right triangle, the orange line would be 1/2 v delta t, because the whole distance from the source to the detector would be v delta t. The blue line would be the height h, and then the red line would be the hypotenuse, which would be 1/2 c delta t, because c delta t would be the distance total that it moves moving from the source to the detector. And so we can do some Pythagorean theorem stuff, write an equation that looks like that, and then we can take it and we can solve it for delta t. And again, please don't feel like you have to write this down. This is just to illustrate what's going on. We don't need to actually know the math behind all this. But anyway, here's the math. So solving for, or I'm going to rearrange this so h squared is by itself. And I'm going to do that so I can factor out the delta t thing. And so delta t squared is now factored out in my equation. And then I can get delta t squared by itself, kind of sort of like that. And then I'm just going to kick the 1/2 up to the top and write it like that. And then doing one of those fancy algebra tricks, I can make it look more like that. And the reason I want it to make it look more like that is this quantity 2h over c is equal to the time that we got before. So I'm going to write it like this: delta t prime squared over 1 minus v squared over c squared. So the time in the stationary frame of reference was 2h over c, so I can just replace that with the original time from the stationary frame of reference, and then I can solve for delta t, and my equation looks something like this. So from the moving frame of reference, the time would have a relationship with the original time over the square root of 1 minus v squared over c squared. And so if you kind of inspect that equation, and you imagine substituting in any velocity that's less than the speed of light, your denominator is going to come out to be smaller than 1, meaning your answer for delta t comes out bigger than for delta t prime, which means the clock would tick slower. And again, that's sort of the big idea here. So as our velocity gets larger and larger and larger, the quantity 1 minus v squared over c squared is going to get larger, meaning that our delta t gets smaller. Except I wrote that wrong. That should be smaller. And that should be larger. So the big idea here, this is what you would want to start writing down again, is that the moving clock runs slower as it gets faster and faster and faster. So to kind of illustrate that in a picture, let's put Annie into a rocket ship that is moving real fast, and let's leave Ben at rest on the Earth. Let's give them both identical clocks, so ridiculously oversized clocks. And so as Annie moves really, really fast, whereas Ben remains at rest, Annie's clock appears to move slower when compared to Ben's clock. So Annie appears to have, or time appears to go slower in Annie's frame of reference, and in Ben's frame of reference it appears to go faster. And so if you were to put Annie in a rocket ship and have her go on a long trip, say to Pluto and back, moving very, very fast, then when she gets back, Ben will have aged much more than she will. And again, it's got nothing to do with biology. It's that time is physically passing slower in Annie's frame of reference. So note in the equation that the velocity can't be larger than c, which means that we would get an imaginary number for delta t. We really can't have imaginary times. The other thing to note about this is that we've actually done these experiments not so much on rocket ship, but using very precise atomic clocks on airplanes. And we have shown that the time difference is exactly what's predicted by Einstein's equation. So for airplanes going around the Earth a few times, we're still talking about a very, very small time difference, like on the order of nanoseconds, but it is measurable, and we have measured it and proven that it happens. Okay, the other thing besides time that's important is space, the actual distance that an object perceives to take up. Things that are in moving frame of references will appear to be shorter, and it's important to note they're going to be shorter only in the direction of motion to an observer who's at rest. So if we take our same rocket ship picture with Annie and the rocket ship and Ben at rest, if we imagine Annie's holding 2 meter sticks, number 1 and number 2, Ben will see the second meter stick number 2, as being shorter than a meter. How much shorter depends on how fast Annie's going relative to Ben. However, he'll see meter stick number 1 have the same length. So when he looks at the rocket ship, it's going to kind of look all scrunched up, like horizontally scrunched up, but he won't notice anything different about the vertical space that the ship takes up. Annie, being inside the rocket ship, sees both meter sticks as being 1 meter long. So she's in the same frame of reference as them. She doesn't notice any difference in their length. In her frame of reference, space hasn't changed any. But she would notice the same difference in meter sticks that Ben were holding. So again, it's not just a trick of perception, it's that space and time are actually different in Annie's frame of reference compared to Ben's frame of reference. Okay, so when is this relativity stuff important? It seems like this is motion, like we learned last year. So again, recall the equation for time dilation looks something like that. So if the velocity is really, really small, like v is much less than c, then the quantity v squared over c squared is essentially 0. And so 1 minus 0 would be 1. The square root of 1 would be 1. And so delta t would equal delta t prime. In other words, when the velocities are small, there's no difference in our perception of time. So time is only important, time dilation is only important, when the velocity is approaching the speed of light. So slow things doesn't really matter. To kind of give you another thing to look at, this isn't really something we need to know, but the equation for relativistic momentum looks something like this. Notice that same square root 1 minus v squared over c squared business going on in the denominator. So again, if your velocity is really, really small, then v squared over c squared is 0, so the denominator is basically 1, and so the equation just looks like p equals mv, like we learned last year in AP Physics 1. Notice also that if the velocity is equal to the speed of light, then our denominator would be 0, more correctly the square root of 0, meaning the momentum would be infinity, which we can't have infinite momentum. It would take infinite force to cause something to have infinite momentum. And so from all that, we can conclude that nothing can exceed the speed of light. That would include objects, and then waves or any other influence. By influence, I mean like ways of transferring information. And so to kind of boil it all down to the nitty-gritty, relativity is only needed when velocities are really, really, really high. An example of something that we have to use special relativity for would be a GPS satellite. Satellites moving in orbit, and they going real fast, they rely on precise timing with the device on Earth they're communicating with in order to know their location. And so special relativity is important in things like GPS satellites. So not approaching the speed of light, but still fast enough that it matters. By the way, the quantity v squared over c squared, because it shows up in all these relativity equations and stuff, is often referred to as the quantity beta. And the quantity 1 over the square root of 1 minus beta is often referred to as gamma. So if you're taking a more advanced class later on in college or something like that, you may see those symbols used. Just FYI. So let's summarize what we need to know, because we've gone a lot further in detail than what we actually need to be able to understand for like our AP exam. So we need to know the two postulates of special relativity. First being that the laws of physics have to be the same. The second being that all observers measure the same speed of light. And again, this only applies in inertial frames of reference. So non-inertial frames of reference where there's acceleration, that's the general relativity thing. So this leads to a couple of different consequences. First being time dilation. Faster you go, with slower time passes. And length contraction. An observer at rest would see objects that are in motion as being shorter in the direction that they're moving. And then the third, nothing can exceed the speed of light. And then it's important we understand what scale to use this at. This is only important when we have velocities which are approaching the speed of light. So high velocity objects can be explained using relativity. It's not really necessary for most things we deal with on Earth as far as mechanical calculations are concerned. So, apologies to all you Star Wars fans. It's not possible for the Millennium Falcon to go 0.6 past the speed of light, which is unfortunate because it would be really cool and awesome. So on that depressing note, ta-ta.